Okay, this is meant to be a lesson on how to use StatCrunch, and I'm going to do it using sort of a sample project. This should mirror somewhat what I'm expecting you to do for your projects. So, the first thing you're going to need to do is to log into Blackboard. So you're going to go to go to the MySuffolk site and click on, log into that, and then click on to the Virtual Learning Commons. Click on to Blackboard, and you will be able to log into Blackboard. I'm already logged in here. Select your course, and you should see this page come up. Alright, now I've added a sidebar item right over here called Project Info. And there are two files that I've uploaded. One is sample data, one is a sample write-up. Now don't click on them. What I want you to do is to right-click on them. You need to save the link. Alright, save as. Save it onto your desktop. Alright, I've actually already done this, so I'm not gonna hit the go button here, but at this point you're gonna put it somewhere on your file system, your desktop or wherever it is you want to put it. Hit save. Alright, I'm gonna cancel out of that. And then you want to do the same thing here with the write-up. Alright, again, save link as. Put it in the same place you put the data. Alright. And then once you have that done, you're going to need to exit out of Blackboard and then come over to my math lab and log in, which I actually haven't done yet. Okay. Again, log into statistics, and then StatCrunch, and then click right here where it says StatCrunch website. Alright, we've looked at this before. Alright, so this is what we're going to use. You need to load the data that you just downloaded. So click select a file from my computer. Over here, choose a file, and then you're going to choose the sample statistics data, which is right here. Alright, now once again, I've already done this, so I'm going to hit cancel. You're going to click on that and hit open, and you will see well, you know what, I should do it. This part won't hurt. Click open, and what you're going to see is just a quick little sample of the data right here. Alright, you're going to go down to the bottom of the page and click load file. Alright, so, what the heck, I'll do it anyway. Alright, and you're going to see this file load. Alright, now, let me explain what this is. I'm teaching 2 sections of college algebra, and one meets early in the morning, the other meets late in the afternoon. And I have given both classes 2 exams. So you can see here I have the grades for the first test for the AM class, for the second test for the AM class, same thing here, first test for the PM class, second test for the PM class. And what I was curious about is whether one class has an advantage over the other. Alright, both classes meet 3 days a week, 2 days a week, Tuesday, Thursday. They both meet on Tuesday and Thursday. And on those days I lecture. On the other 2 days, one class meets on Monday for a shorter period of time, and we use that time to go over homework and answer questions. And the other class meets on Fridays. Again, same thing. We go over homework, answer questions. The AM class meets Monday, Tuesday, Thursday. The PM class meets Tuesday, Thursday, Friday. So there are a couple of reasons why I might think one class has an advantage over the other. I'm doing a lesson first with the AM class, and if I find something that doesn't work with the AM class, I may do it differently with the PM class. Also, if I, run into any mistakes that I tend to do on the board in the AM class, I'm less likely to make those mistakes in the PM class. Also, because our extra help day on the AM class is on Mondays, early in the morning, I tend to have more students show up than I do late on a Friday afternoon for the PM class. So the AM class is taking more advantage of the extra help than the PM class is. And I want to see, based on these two exams, if it looks like one class has an advantage over the other. All right. So I'm going to pull up the write-up here so we can look at this. Now, when you get your project, it is not going to be this data, but when you get your project, I will give you a page just like this one. All right. So using the data collected from 2 college algebra classes, 1 early morning class, 1 late afternoon class, I would like to determine several things. The overriding question is, does one class have a significant advantage over the other, and if so, which class has the advantage? The data consists of grades from 2 exams. Each exam was administered to both the AM class and the PM class on the same day, and the exams were given approximately 3 weeks apart. All right, so that is, the first exam was administered to the AM class and the PM class on the same day. The second exam was administered to the AM class and the PM class on the same day. The 2 exams themselves were given approximately 3 weeks apart. All right, the AM class has 34 students in it, the PM class has 36 students in it. So to answer the overriding issue as to whether one class has an advantage or not, I'm going to have to answer several questions. All right, so the first one, first and foremost, are the test scores approximately normally distributed? And I'm going to use an alpha of 0.1 to determine that. Mostly because they don't need to be exactly normally distributed to do what I want to do with them. All right, I just need them approximately, so an alpha of 0.1 is fine there. So the second question is there any correlation between the 2 tests for each class? It would be interesting to know if students who did well on the first test did well on the second, or if students who did well on the first test did poorly on the second, if students who did poorly on the first did better on the second, so things like that, with an alpha of 0.05. So I'm going to use an alpha of 0.05 for the remainder of this. Now, to get to the actual questions. Now, did the students score better on one test or the other for each class? All right, so that's one thing I want to know. Did one of the classes score better than the other on each test? All right. And then, is there a difference in the variability of the scores from class to class and from test to test? All of that I'm going to test at an alpha of 0.05. All right. So when you receive a data set like this, the first thing you want to do is to start making determinations as to who you think might have done better than the other, or which variable you think has a higher mean than the other, which variable you think is more variable than the other. So in this case, what I'm going to do, and what you should do when you first get your data set for your project, is to run a basic set of statistics. So we come over here to StatCrunch, click Stat, Summary Stats. All right, Summary Stats, the variables are the columns, so the summary stats are going to be run on the columns. Now the summary stats you can see down here, things like mean, variance, standard deviation, range, median, all of that sort of thing. All right, I'm just going to leave all of these highlighted, and I want to do it for all 4 variables. So I'm going to highlight the first variable, go down to the bottom, hold down the Shift key, and highlight the last one. You'll see all 4 variables move over here. All right, there's nothing else that I need to do on this. I'm just going to hit compute, and what I end up with is this nice little chart that gives me for test 1 AM, test 2 PM, all AM, PM, all that stuff. The means, the standard deviations, and the medians are the important bits of information that I'm interested in. So the first thing that I did over here on the write-up was to make some observations about the summary statistics. So I pulled out the mean, the standard deviation, the median, and the n for each one. All right, and one of the things, I noticed a few things. Now what this is going to help me to do is it's going to help me to clarify the general questions that I have written on the project page. All right, so I can look at this now and I can see the means for both test 1 and test 2 are higher for the AM class than they are for the PM class. So then the question I want to know is, are they significantly higher? The means for test 1 are higher than the means for test 2. Are they significantly higher? And then as far as variability goes, the standard deviations for test 1 and test 2 are higher for the PM class. So are the PM grades more variable than the AM grades? And the standard deviation for test 2 is higher than test 1 for both classes. So are the grades for test 2 more variable than the grades for test 1? Okay. All right, so what that does is it takes the general questions that I asked up here, is there a difference? And by looking at the means and looking at the standard deviations, I can determine, well, it looks like there's a difference and this one looks like it's higher. So now I can test specifically for which one is higher than the other. All right. Okay, so we don't need this anymore. I'll put that away. All right, now, so the first question I want to determine is the first question on my list, which is, are the data normally distributed? If they're not, then I can't go any further. So I need to have a way to check to see if my data is normally distributed. And there's a way to do that. Go into Stat, down here to Goodness of Fit, and right here is the normality test. Right. Now we're going to do two things. First of all, we need to test all 4 of the variables. So all 4 of the variables go over there. Now that'll give me a correlation coefficient, a coefficient of determination, and a p-value on the slope of the linear regression line. The only other thing I want is a visual. All right, so I'm going to do a QQ plot, and I'll explain what a QQ plot is when we look at it. And then I'm going to hit compute. So now if you look here, right, and I summarized the important bits here. Okay. For the oh wait, this one doesn't give me the coefficient of determination. That's another test. Hang on. All right, what I get here is a correlation between the data, the z-scores for the data based on the mean and standard deviation, and the z-scores of what the normal plot should look like. All right, so I end up with basically all these correlation coefficients and these p-values here, which again I've summarized in this table so we can look at it side by side. Now as far as the QQ plots go, all right, this line right here represents the yeah, there it is, in fact, what the linear regression line should look like. Okay, and we're comparing again the test scores to the z-scores for the categorized data. If you were to list the data from smallest to largest and rank it, so I guess ranked data is a better way to say it. Just like you would do for percentiles or something like that. Anyway, it doesn't matter. What you're looking for here is a basic linear pattern. All right, which you can see there's some down here that are off, there are some up here off, but the bulk of the data is gathered around the line. And if we look at that for each one of these, all right, you can see while there's some data that's off up at the top end and the bottom end, most of it is linear. Now where we start running into a few issues with the PM class is in particular right here. And what I had was 3 students who did not show up for the exam. I actually believe they're dropping the class. I don't think they've done it yet, but that doesn't matter. They were still registered for the class at the time the exam was given, so they ended up registering a grade of 0. Now that may come back to bite us a little bit later on with some of the results, but we'll see, because most of the data is, you can see, linearly related to the to the ranked z-scores. All right, so that's just a visual inspection. Okay, so now I took this over here. We can see what I can get from this. So I've got the normality goodness of fit test results summarized right here. All right, so for the first test, we've got a 91% correlation with the z-scores, which is good, and a p-value of 0.007, which is significantly below my cutoff alpha. All right, so I can make a conclusion there that there's enough evidence to suggest that these data are approximately linearly related. For test 2, for the AM test 2, I've got again, a correlation coefficient of 94% and a p-value of 0.08, which is, again, below my alpha. For test 1 for the PM, I've got a correlation coefficient of 0.89 and a p-value of 0.002, also below my alpha. And for test 2 for the PM, I've got a correlation coefficient of 94% and a p-value again below my alpha. All right, so given that the correlation coefficients are relatively high and the p-values are all below 0.1 and the QQ plots are approximately linear with no significant outliers, except for test 2, it is safe to conclude that the grades are approximately normally distributed, though outliers do exist in the QQ plot for the PM class test 2, and we'll see how that might affect us later on. All right, so I can put this one away. All right, so the next question I want to take a look at here is, are there any correlations between the grades received for test 1 and test 2 for either class? Right. So there's two things that I can do to make this determination. The first one is to actually do a regression analysis, which we'll do, and the second one is to look at a scatter plot. All right, so let's look at the AM class, test 1 and test 2. If I go over here to graph, now notice I've got all these graphs I can do. I want to do a scatter plot. And I am going to select my variables up here, test 1 for the AM class, test 2 for the AM class, because remember, Scatterplot is dependent data, so I have to compare class by class. I'm going to leave everything else alone, and I'm going to compute. All right, so I end up with something that looks like a cloud, right? It doesn't look like a strong linear correlation, but it is trending upward. All right, it does have an upward trend to it. All right, so I'm going to move that over, and I'm going to go over here to stat, and I'm going to go to regression and simple linear. Okay, and I'm going to pick the same two variables, test 1 AM, test 2 PM, test 2 AM, sorry. Now I'm going to leave the hypothesis test in there because that's going to give me something to look at. All right, so remember, when we're doing regression, hypothesis tests for the slope is what we're interested in. The slope is either 0, there's no linear correlation, or it's not 0, there is a linear correlation. And again, everything's at 5%, so 95 is where you want to leave that. Hit compute. All right, and let's see what we get here. All right, so right next to our scatter plot here. All right, so we've got our dependent variable, our independent variable. It doesn't really matter which way we label those. We've got our correlation coefficient is 0.46. That's not really that high, but it is positive. And we've got an r squared, right? Our coefficient of determination is 22%, let's say. All right. And then, wait, I need the p-value, don't I? Okay. The p-value for the slope is 0.005. So if I'm using 0.05 as my cutoff, that's actually indicating that that a linear correlation is the best fit. It's not a high one. It's certainly not a high one, 47%, and only 22% of the variation can be explained by the linear correlation line. All right. And what I can do over here is show you the write-up for this part of it. Okay. So the correlation tests result in the following. The correlation tests result in the following. Gotta fix that. The AM class has a correlation coefficient of 0.47 with a p-value for the slope of 0.005, and a coefficient of determination for 0.22. Alright, the correlation is extremely low. Typos. The correlation is extremely low, with only 22% of the variation described by the regression line. The p-value is less than 0.5, which suggests that a linear regression is the best fit, but with a very low correlation. All right. The scatter plot bears this out. Now let me just point something out here. Let me close this. To get the scatter plot from here into my graph, all I did was come over here, right-click on my scatter plot, select copy the image. All right, then I moved over here and I right-clicked and I said paste the image. So you can take any of these tables, any of these graphs, and copy and paste them into a Microsoft Word document or a Open Office or Google Docs or whatever you want to paste it into. Okay. All right. So we have a low, really low correlation, but an upward trend here. And if I do the same thing for, I'm going to show you a trick with this after this one. For my PM class, you're going to see something similar again. The data looks mostly like a cloud, but there is an upward trend to it. All right, and then again, we're dealing with these three outliers down here. They took the first test, didn't take the second, and I had one student who took the second test but didn't take the first. All right, so there are 4 zeros involved in this. All right, so again, we have an upward trend. And if I calculate the linear regression, same two data values, with the hypothesis test, I get a correlation coefficient of even lower, right? 0.37, 0.38. A coefficient of determination of 0.14. Alright, so that means there's about a 37% correlation linearly, and only 14% of the variation can be explained by the regression line. But again, the p-value is 0.02, which is below my alpha value, meaning that the linear correlation is the best fit for this data. And again, you can see that with the chart, because there's this upward trend. There's not any other sort of shape to it. All right, so written up down here. All right, the PM class has a correlation coefficient of 0.38 with a p-value for the slope of 0.02 and a coefficient of determination of 0.14. The correlation is extremely low. I did it again. Extremely low, with only 14% variation described by the regression line. The p-value is less than 0.05, which suggests linear regression is the best fit, but with a very low correlation, and the scatter diagram bears this out. So the question is there enough evidence to suggest that there is a linear correlation or a significant linear correlation between the two exams? There's not enough evidence to suggest that there's a significant linear correlation between the grades for test 1 and test 2. There's a very weak one, but there's not really a significant one. All right. Okay, so let's get rid of this. Let's get rid of this. All right, what's the next thing we need to do? Did the AM class score significantly better on either test than the PM class? All right, so here's where we start getting into the guts of the main question. Okay. All right, so to answer this question, you have to perform a 2-sample t-test with data for test 1 and test 2. All right, so in this case, here's what I'm setting. All right, I'm just gonna spoil it here. Here's what I'm setting up. All right, group 1 is the AM class, group 2 is the PM class. My 2-sample t-test for T1 is going to have my null hypothesis that the two means are the same. Remember, I'm asking, did the AM class score better, higher? All right, so my H1 is going to be that the mean for group 1 is higher than the mean for group 2. All right, so you go over here to Stat, t-test, 2-sample with data. All right, now keep in mind, these are not paired samples because we're comparing 2 different groups. Okay, so test 1 for the AM class, test 1 for the PM class. And what are we going to do here? We're going to take off the pooled variances, though that doesn't really make a huge difference. And come over here, we're looking for greater than. Right, this does the subtraction thing, so it's still greater than, though. And then hit compute. Okay. So what do I end up with here? Well, get my sample difference mean, I get my standard error, my degrees of freedom, my t-stat, and in particular, what I'm looking for, I get my p-value. All right, so in this case, the p-value is 0.2984, so I'm going to round that off to 0.30. All right, so come back over here, right? The p-value is 0.30, which is greater than 0.05, so there's not enough evidence to suggest that the AM class scored significantly higher, right? We're not rejecting the null hypothesis here. All right, now we can perform the same test for test 2. Now, I'm not going to close this and open up a whole new test. If you go over here to Options and Edit, it pulls this back up again, and I can simply make the change here. I don't need to save it necessarily. You know, if I'm taking down all my information. Save it if you want to be able to copy and paste it into the document, but for the sake of this, because this way everything else is already set up. Okay. All right, so for test 2, again, I have the same 2 hypotheses, right? All right, so that there's no difference between the means, or that group 1 had a higher mean than group 2. All right, this time my p-value comes out to be 0.0142, so 0.01. So the p-value is 0.01. That's less than 0.05, which is my alpha. So there is enough evidence to suggest that the AM class scored significantly higher on the test than the PM class did. Okay. So we can't make a conclusion. We can't draw that conclusion for the first test, but we can for the second test. All right, and we'll talk about what that means in a little bit. All right, so now the next question is, were the grades for the first test significantly higher than the grades for the second test? All right, so to answer this, I have to flip around my variables. All right, so to answer this, I'm going to perform a paired sample t-test, right? Because now I'm comparing within a class. All right, so I'm going to get rid of this because now I have to do a different test. So now what I want to know is, are the grades over here significantly higher than the grades over here? Did the students from my AM class do better on the first test than they did on the second test? And then I'm going to repeat that for the PM class. So to perform that test, first of all, we set up our groups, right? Group 1 is going to be test 1. Group 2 is going to be test 2, because that's what I'm comparing, test 1 to test 2. Set up my null and my alternative hypotheses. And now I'm still performing a t-test, but now I'm performing a paired sample t-test, because this is dependent data. So test 1 AM, test 2 AM. Alright, now you have the option here of saving the differences. You know, when it does the calculation where it subtracts you know, group 1 minus group 2 to get the paired differences. I'm not going to bother doing that here. I don't need that. But what we're looking for is if the mean for group 1 is higher than the mean for group 2, then when I subtract group 1 minus group 2, that mean should be greater than 0. Okay, so I get that. And again, I'm going to leave everything at 0.05. And I'm going to compute. Okay, so again, the important thing here is the p-value. Just verify that this is all correct. Alright, the p-value is 0.18. Alright, so if the p-value is 0.18, it's greater than 0.5, so there's not enough evidence to suggest that the mean grade was higher on the first test for the AM class. Alright. Now I want to do the same test for the PM class, so again I set up my hypotheses, and I'm going to switch this now over to the PM class. Everything else remains the same. That's one of the advantages to just going back and editing. Hit compute, and again everything else here is right. So my p-value is 0.0028, so round that off to 0.003, and that is less than 0.05, my alpha. Alright, so for this one we can reject the null hypothesis. There is enough evidence to suggest that the mean grade was higher on the first test for the PM class. And again, we'll talk about that in a few minutes. Alright, so we've got information. Right, we've got information about where we think which grades might be higher. So the next thing I want to look at here is the variability. Alright, so are the grades for the PM class more variable than the AM class for each exam? Alright, and we're going to do that again at an alpha of 0.05. So okay, so group 1 is going to be the AM class, group 2 is going to be the PM class, because that's what we're comparing. Alright, we're going to do it for each exam. Alright, so remember, when you're testing variability, you're doing an F-test. Alright, so I'm going to do an F-test for test 1. And with an F-test, we're looking at these standard deviations. So I am interested in, well again, my H0 is that there's no difference in the standard deviations. My H1 is that there is a difference in the standard deviations, and that that the PM class is more variable than the AM class. Right? Alright, so to do a test for variability, you go to Stats, Variance Stats, and toSample with data. Okay. Now we're going to do, what are we doing here? We are doing for test 1s, we want to know if the AM's test 1 and the PM's test 1 are different. Alright, now since we have the actual statistics, I know how to set this up, right? I want to know if, okay, so now again, they're doing the ratio, and I have written that one is less than the other. So if sigma 1 is less than sigma 2, that means sigma 1 divided by sigma 2 is less than 1. Alright, so I want a less than there. Everything else can sit, and I'm going to compute. Alright, so I get all of the information here, and I get a p-value of 0.15. Alright, so I come over here, I'm going to just pull this all up. Alright, I get a p-value of 0.15, which is greater than my alpha. So there's not enough evidence to, so I can't reject my null hypothesis. There's not enough evidence to suggest that the grades for the PM class on test 1 are significantly more variable than the AM class. Alright, now I'm going to do the same test again for test 2. Alright, so I can come back over here, edit, and I'm going to switch both of these to test 2. I'm going to click the go button again, and this time I end up with a p-value of 0.0627. Alright, so where is this one? Here it is. Okay. So the p-value is 0.06, which is greater than, only just slightly, but it is greater than my alpha. Alright, so there's not enough evidence to conclude or to suggest that the grades for the PM class on test 2 are significantly more variable than the AM class. However, notice how close the p-value is to the alpha. Alright, if I were to test this at even just our other standard alpha value of 0.1, alright, if I was willing to accept a 10% chance of making a type 1 error, type 2 error, I would actually have to conclude that there is enough evidence to suggest that the grades are more variable. Alright, so I've made a decision that 5% is my cutoff, and I think 5% is reasonable for this. Alright, so while there is not enough evidence at the 5% level to suggest that there's a difference, it's pretty close. Alright, and again, we'll talk about that. Alright, so then the last question we've got here, I hope it's the last question. Yes. The last question we've got here is, are the grades for test 2 significantly more variable than the grades for test 1? Alright, so now we're looking at test 1 and test 2 as our variables, and we're going to be looking at the tests for the AM class and the PM class. This doesn't go directly towards answering our question, but actually I could have just used that. Alright. But it's possibly relevant, so we'll see. Alright, so I go back to my variance to sample with data, and I've set up my hypotheses here again. Alright, F-test for the AM class we saw from the statistics, from the summary statistics, alright, that the standard deviation looked to be higher. Alright, so we just want to see if that's significant. So what am I doing here? I am doing test 1 for the AM class, and I am doing test 2 for the AM class. And I am interested in this going that way. And compute. Alright, so we end up here with a p-value of 0.2237, so I'm rounding that off to 0.22. Again, greater than 0.05. Since it's greater than 0.05, there's not enough evidence to suggest that the grades for test 1 are significantly more variable than the grades for test 2 for the AM class. I repeat the same test for the PM class. Just do it this way. Test 1, test 2, hit the go button, and I end up with 0.0915. Alright, so 0.0195 is my p-value. It's greater than my alpha, so there's also not enough evidence to suggest that the grades for test 1 are significantly more variable than the grades for test 2 in the PM class. I have to fix that. In the PM class. Okay, but again, notice it's still fairly close. Alright. Alright, so let's pull all this together and see what we can say about it. Alright. Now, first thing I need to address are those outliers in the PM classes test 2. So I just need to make a statement about that. And while I was able to establish all of the tests are approximately normally distributed, there are outliers in the data for the PM classes test 2 corresponding to students who received a grade of 0 for not taking the exam. Alright, so this is going to end up affecting my outcome. Alright, the data showed a weak linear correlation between test 1 and test 2 for both classes. While there was no significant difference between the two classes on the first test, there was on the second, with the AM class scoring significantly higher at a 5% level of significance. There was not significant evidence to suggest that there was any difference in variability between the two classes or between the two tests. So I don't have a whole lot to go on here. I have one exam that is showing possibly one class scored higher. So, does one class have a significant advantage over the other? I would have to conclude that there's not enough evidence to suggest, based on this data, that either class has an advantage. Even though the two sample T test indicated that the grades were higher on the first test and that the AM class scored higher than the PM class, number of outliers in the PM classes test 2, I believe, invalidate those results. All right. Okay, I know I went through this kind of quickly. I am going to go through it much more slowly in class, but I want you to use this as a model for, first of all, what I'm going to give you on the project and what I expect to see you do for a write-up. It's not going to be quite this long, right? I promise. I did a much longer and probably a little more involved analysis than you're going to need to do. But you can use this as your model. Okay, we'll see you all on Tuesday.